this lesson finishes up section 10.3. So we're interested in finding derivatives when we have polar equations. Okay, so if we have that the radius is given as a differentiable function of theta, our goal is going to be to find a formula for dy dx in terms of the angle theta. So if you're thinking about plotting, as we were yesterday, we were thinking about we would go to the angle theta, we would find what the radius was there, and we'd plot a point. It would be really helpful for us if we were able to draw a little line segment showing what the tangent line is going to be. That would help us fill in this picture more accurately, right? And we think naturally sort of in terms of dy dx, so we want to know what the slope is in terms of x and y at a given angle. Okay? All right, so we have our equations that x is equal to r cosine of theta. And again, remember that we're thinking of r as a function of theta. And we know that y is r sine theta. And again, we're thinking of r as a function of theta. Okay, so this describes our curve parametrically in terms of the parameter theta. Parameter theta. All right, so when we talked about finding dy dx, when we had a parameter for a parametric equation for x and y, we said that to calculate dy dx, we could calculate dy d theta and dx d theta. So that's what we're going to do here. Take the ratio of dy d theta and dx d theta. Okay, so we're going to do that calculation on the side. We know that y is r of theta times sine theta, so we're going to use the product rule to differentiate this. We get that dy d theta is dr d theta times sine theta plus r of theta times cosine theta. And we can use that x is equal to r cosine theta to say that dx d theta is dr d theta times cosine theta plus r times negative sine theta. Okay, and so in the end, we have this formula dr d theta times sine theta plus r cosine theta over dr d theta times cosine theta minus r sine theta is our derivative dy dx. All right, let's try out an example.